Hello everyone and welcome to another video. So today I wanted to have a quick discussion on matrices. So matrices make up a lot of fundamental mathematical and engineering concepts. So today I wanted to take a very high level overview of what matrices are, how to manipulate them. We are going to save kind of in-depth discussions of matrices and their operations to future lectures. So for today it's really almost like a high school refresher of what is a matrix, how do we use it, right? So to start with that, a matrix, it's actually a surprisingly simple concept, right? All a matrix is, it's a two-dimensional array of numbers. So it's just numbers or symbols or however you want to think about it, arranged in rows and columns, okay? So that's the simplest definition of a matrix. Again, just a two-dimensional array of numbers, okay? If we have that in place, I'm sure the next thing on your mind is, okay, if I've got this two-dimensional array of numbers, how do I maybe refer to a specific element inside this array, right? Well, I'm glad you asked that question. A lot of the times what you're going to see is notation like this. You'll see A sub ij, okay? So the subscripts here, ij, the I refers to the row number and the j refers to the column. So in this case, aij, it's the element that is in the ith row, the jth column, okay? So then we'll look at some examples, okay? I just want to note this right now for a completeness sake, okay? So that's how to get into a specific element or reference one element of a matrix. Another thing that's a characteristic of the matrix that I'm sure you're going to be interested in is just the overall dimension of the matrix. A lot of times you're going to hear people refer to the dimension of a matrix. So the matrix dimensions are just the number of rows by the number of columns. So in this case, we have m rows and n columns. All right, so that's what we say is this is an m by n matrix, right? Great. So a special type of matrix is a matrix that only has a single row or a single column. So in this case, you can kind of think of it like a single column would be like if I covered up all of this stuff and you only had one column, or if a single row would be you cover up all this bottom stuff and you only have one row. Okay? So if you end up with a matrix that only has a single row or a single column, a lot of times that's referred to as a vector, right? And again, you can think about it as a vector is just a special type of matrix that only has a single row or a single column, okay? From a notation perspective, you'll see a lot of textbooks and references kind of make a slight distinction between a full 2D matrix and a vector. You'll see notations of usually it's capital letters are used to refer to as matrices. So capital A, capital B, capital C, that is a matrix that has multiple rows, multiple columns. If you have a vector, what you'll see a lot of times is people use lowercase letters, but then they'll denote it with like a bar on top, or they will write that lowercase letter in big bold face. So I know it's a little hard to do that on the board. So what I typically do is I use a bar on top to denote a vector. So again, capital letters are usually reserved for matrices. Lowercase letters that are decorated with a bar on top or boldface are used to denote vectors, okay? So the reason it's nice to think about these things as being built up as rows and column vectors is you can build matrices using these single row or column vectors. So a lot of times it's very useful to think of a matrix as nothing more than being comprised of a bunch of row vectors stacked on top of each other like this, or a bunch of column vectors stacked next to each other like this, right? So again, in this picture we have an m by n matrix. I could think of this matrix as being comprised of here's the first row, here's the second row, all the way down to here's the mth row, and they're all just vertically concatenated on top of one another like this. Or you could think about this matrix as here is the first column, then horizontally concatenated with the second column, blah, 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 horizontally concatenated with the nth column, as you see here, right? So this is going to come into play a lot later when we start talking about the range and the span and the spaces of these different matrices. This is going to be a very helpful representation. But again, for now, just think about it as a way to build matrices is by basically stacking rows or columns next to each other, okay? So let's look at a very simple example just to make sure we're all on the same page. Let's consider this matrix right here. So it's just 1, 3, negative 1, 0, 3, 5, okay? So you can see right off the bat the dimensions of this matrix. It's a 2 by 3, right? Because there are 2 rows and 3 columns. And for example, the element in the second row, third column, that is here, right? You go second row, 1, 2, third column, that's this entry right here, right? That's just 5, right? So pretty darn easy, okay? And again, you could also think about this matrix A as just being 2 rows. Row 1 here is maybe what I'll do in blue here, right? Here's row 1. And then row 2 could be stacked underneath of it here, right? So here's row 2, right? So that's one representation, as you can think about it, as just 2 row vectors stacked one on top of the other. Or, like we saw earlier, I could also just as easily, instead of thinking about these as row vectors, I could think about them as column vectors. So instead, I'm going to now think about this. Whoops, sorry, I think I erased a little bit too much, but I think you get the picture right. So here's the first column, C1. Here's the second column, C2. And here's the third column, C3, right? So I could horizontally concatenate them one after the other, right? Okay, so that's the general idea with matrices. Let's go ahead and give me a second to erase the board, and let's talk about some operations we can do on them. All right, so the first thing I'm sure people are going to want to do with a matrix is add or subtract 2 matrices, okay? So this is actually really simple. If you want to do that, it's going to require that both of these matrices that you're manipulating have the exact same dimensions. For now, let's assume that it's m rows by n columns. So both matrices need to have that same dimension, okay? So if you do addition and subtraction on these 2 same size matrices, no surprise, you're going to produce a matrix of that exact same size, namely m times n, right? Okay, so the size is not going to really change too much. So to go ahead and do this add and subtraction, all you simply do is you do add and subtraction on each element. This is sometimes referred to as an element-wise operation. So in other words, theCijth element, which is just going to be Aij plus or minus Bij. So depending if you're doing matrix addition or subtraction, you just do this, right? Again, I think we're overstating the fact, right? This is a really simple idea, right? And I think you can see that if we just look at a very simple illustrative example. So let's look at A and B, okay? So first thing to check is, are these dimensions the same? Again, and one thing that you're going to be, that I find to be a helpful little tool is, I like to write down the dimensions underneath. So this is obviously a 2 by 3 matrix, right? Same thing with B. It has 2 rows by 3 columns, right? So great. The dimensions of these two things match. So it's going to produce a matrix that is also 2 by 3. Okay, let's look at how about doing, I'm going to call this C plus, where all I want to do is add A and B together, or do addition, right? So all you do is, to get this 1, 1 element, right, you take the 1, 1 element of A, you add to the 1, 1 element of B, and you get 3, right? And then you take the 1, 2 element of, 1, 2 element of A, add to the 1, 2 element of B, you get the 1, 2 element of C, right? And yada, yada, yada. This is really simple, so I'm not going to belabor the fact, right? So you just add each element element-wise. And same thing for subtraction. You just subtract each element element-wise, right? So 1 minus 2 gets you negative 1. 3 minus 4 gets you negative 1. Negative 1 minus 2 gets you negative 3, etc., 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 right? Okay, so great. So if that's all it is, let's talk about, you can write down some very simple rules for matrix addition here. So if you add 2 matrices, A plus B, it's the exact same thing as B plus A, right? The order doesn't matter in matrix addition, correct, right? Same thing. If we're talking about adding multiple matrices together, the order in which you do that addition, it doesn't matter. You can add A to B first and then add C, or you can add B to C first and then add A. It doesn't matter in this case, right? Okay, if you have A plus, this is sometimes referred to as a 0 matrix. Sometimes you'll see this written as 0, like with the dimensions in a subscript, like m times n. So you have an m by n matrix adding to a 0 matrix of m plus n. Again, this is just a matrix filled with zeros. And as you can imagine, you just get A back in this case, okay? And then similarly, if you go ahead and you take the negative of the matrix, basically take the negative of every single element, you add it to itself, you're going to get this 0 matrix back. So again, let's just brush over this because this is really, really simple. This is, again, back to kind of, this is going back to middle school, right? And I'm sure you can get a very similar set of rules for matrix subtraction, which is basically this. I think you might have to do something like, I think it's A plus B, or sorry, A minus B is like negative B minus A, right? But again, this is exactly like you have seen in scalar subtraction, so nothing different right here, okay? So let's move on to something more interesting. All right, so let's move on to matrix multiplication, and this is where it gets interesting. And when I say interesting, I mean it gets a little bit ambiguous because depending on who you're talking to and in what context, matrix, quote unquote multiplication might mean one of three potential different things. So basically there's three different types of matrix multiplication, which they all behave very differently. So I think what would be most useful is let's go through each one of these three individually and we can learn their nuances and understand their differences. Okay, so the three different types of matrix multiplication are: one, what's sometimes referred to as quote unquote, standard matrix multiplication. Two, you could also be talking about matrix element-wise multiplication. And lastly, you could be talking about matrix scalar multiplication. Okay, so let's talk about each one in order. The first one is probably the most common, and it's also kind of the most maybe complicated if you want to think about it that way. But this is what most people mean when you read a math textbook or see some reference and you see something about a matrix multiplication. 8 out of 10 times we're talking about this standard matrix multiplication, okay? So let's look at that now. So standard matrix multiplication, again, the nomenclature that you'll see is, pretty standard. It's A space B, or, maybe, I really hesitate to put a dot in here, and you'll see why later, but I'm just trying to illustrate that a lot of times this is just what you would see when you're trying to multiply two numbers together or two variables together, or in this case, two matrices together. It's just capital A times capital B, right? Produces something called capital C, right? So two matrices produce another matrix using this multiplication, okay? So what's interesting about this is, let's look at this first bullet, right? In order to do this operation here, we are going to see that these dimensions of A and B need to be consistent. They don't need to be the same, they need to be consistent. What I mean by consistent is that these matrix A, let's look at it. Let's assume this has a dimension of m by p. So I'm going to write underneath of it m by p. Okay, that's the dimension of matrix A. Okay, in order for this to have any chance of working, B here, it has to have p rows. I don't care how many columns, but it must have p rows. Let's assume it has maybe n columns, right? So B is of dimension p by n. Okay, what happens now is that when you do this, these dimensions are consistent. What it will produce is this will produce a matrix of size m by n, okay? And a handy mnemonic that I've discovered that helps me remember if matrix multiplication is legal or not is that these two inner dimensions here need to match, okay? So these match, okay? If these two match, what's going to end up happening is you are then going to be able to produce a matrix of the outer dimensions, right? So this produces the dimension C that we see over here, right? So again, we'll see some examples, and you'll see why that is when we start talking about how this matrix multiplication actually operates. So again, this is just a quick check to see if the dimensions of A and B are even consistent so that you can perform this matrix multiplication to get the matrix C, okay? All right, so provided your dimensions are consistent, to get this matrix C, it's actually kind of interesting the way you do this, okay? So the ijth entry in C is computed by taking the inner or the dot product of the entire ith row of A with the jth column of B, okay? So again, I'm going to assume that maybe you remember a little bit about this idea of inner / dot product. We have a completely separate video talking about dot products and other vector mechanics, but you're going to see it's actually really quite a simple operation, and we'll go over this in detail. So feel free to check out this other video if you'd like to dig further, but really it's not a prerequisite to kind of proceed. I just want to put this bullet down here so we have the definition down. Let's now jump over to the example and see exactly how you compute this, okay? So here's my example. Let's say you've got this A matrix here of, I guess I filled it in with just a bunch of odd numbers, right? 1, 3, 5, 7, 9, 11, okay? And B is another matrix filled with even numbers, 2, 4, 6, 8, 10, 12, right? Okay? So the first thing we should do is let's ask ourselves, can I multiply A with B, okay? So first things first, let's go ahead and get the dimensions of A, right? You see, this is clearly a 2 by 3 matrix, okay? B is clearly a 3 by 2 matrix, okay? So let's go ahead and do our little handy mnemonic and ask ourselves, hey, is this even legal? So A is of size 2 by 3. B is of size 3 by 2. So the first thing we got to do is we got to check, do the inner dimensions match? And they do, right? So this matches. So good, that's a check mark. We are clear to proceed, right? What this is now going to do is once I go ahead and do this matrix multiplication, I know it's going to produce a matrix of the outer dimensions. So in this case, we're going to get a nice square matrix of size 2 by 2. So this C matrix, I know at the end of the day, it's going to be a 2 by 2 matrix. Okay? So there's our dimension check out of order and complete. So now let's just write this out, A and B. So here's A, here's B. Let's just write them next to each other. And we know this is going to produce a C matrix over here on the far side, which is of size 2 by 2. So maybe what we can do now is let me draw a couple of lines here, right? We know that this is going to be a 2 by 2, right? Okay? So now the question is, how do we get each of these elements, right? So I need to compute these 3 elements. Whoops, you just dropped my pen. We need the C11, the C12, the C21, and the C22 element, right? Okay, let's go ahead and look at this first one, C11, right? Okay, so the way we get C11 is, according to our definition over here, it's you take the inner product or the dot product of the ith row of A with the jth column of B. So in this case, it's the first row of A and the first column of B. So let's just identify what those look like over here. Which ones are we talking about? Let me erase some of this so we get a little bit more room. Okay, so I am dealing with the first row of A, that's this guy here in blue, right, with the first column of B, okay? So all you have to focus on in order to get this 1, 1 element, it's just row 1, column 1, okay? So if you remember, this you can think about as just a row, right? You could think about this as row 1, right? And I could think about this as column 1. So it's just 2 vectors, right? Does everyone remember how to take the dot product of 2 vectors, right? So what we're really talking about is I want R1 dot product with C1, right? Which really is nothing more than the summation of each one of these elements, right? Column I, right? From I equals 1 to however many elements there are, right? So really all we're talking about here is let's just write this out to be explicit, right? This element, it's just 1 times 2, right? So here's 1 times 2. So it's the 1, 1 element of the vector times the 1, 1 element of that other vector plus the the second element, right? So this is 3 times 6 plus third times third, 5 times 10, right? So this gets me, this is this inner product or this dot product, right? It's just you do this multiplication and what do we end up with? This is 70, right? Okay, so now let's get a little bit more practice, okay? Let's get the C12 element, okay? So now I'm talking about, let's focus on this element, okay? So now the only thing that changes, right, is we said, I now need to look at the first row of A and now the second column of B. So let me change this bracketing. So first row of A, but now I actually focus on this column. Okay, and now I do the exact same operation. Okay, so it is now the first element times the first element. So it's 1 times 4, right? Plus second element times second element, 3 times 8, plus third element times third element, 5 times 12, right? So you do that and you end up with 88. Okay? All right, now let's keep going, okay? Let's get the C21 element, okay? So now we are focusing down here, okay? So again, now I need the second row of A and the first column of B. So I got to change my bracketing completely, right? I am looking now at these ones here, right? I care about the second row of A and the first column of B, right? And now we just go ahead and say first element times first element. 7 times 2 plus 9 times 6 plus 11 times 10, right? And you end up with 178, okay? And let's do practice for the last one just for the sake of completeness. So now we are focused on this element right here. So I need the second row of A and the second column of B, so I got to change my outlining of what I'm dot producting. It's this one right here, right? Okay, so it's now what? It's 7 times 4 plus 9 times 8 plus 11 times 12, and you end up with 232, right? So at the end of the day, this C matrix here looks just like, here, we can just fill in these numbers, right? It's just 70, 88, 178, and 232, right? There we go. Okay, so that's how you do this standard matrix multiplication. Okay, so now that we understand this, maybe what we can write down is one of the most common fundamental rules for this matrix multiplication is, and I'll leave this as an exercise for the viewer, right? But we see that in general, AB is not equal to B times A. Okay? So do not make this mistake, right? What is so insidious about this, right, is that obviously if A and B are just scalar numbers or variables, it doesn't matter which order you multiply them in, right? However, in this case, it does, because really the thing that's different, right, is this operation that we're talking about doing here, the implicit, this white space between the A and B, right, it implies matrix multiplication, which is not standard, just normal multiplication, right? It is this kind of interesting inner product of row and column behavior. So really, this is where maybe the nomenclature is misleading to people that are first getting into this field, right? Is when you say quote unquote standard matrix multiplication, you are not doing standard multiplication by any means, right? You're doing this inner product, dot product of rows and columns. So you get interesting properties like this, right? This does not look like standard scalar multiplication, right? This is interesting, right? And it has ramifications down the road, okay? Now, that being said, I think this leads into our next discussion. Let's examine what is sometimes referred to as matrix element-wise multiplication. Okay, so I actually haven't erased any of the board right now because I want you to see the differences live. I don't want anything to kind of disappear. So what we're talking about here is, let's switch this now, and instead of standard matrix multiplication, let's look at item number 2, where this is now element-wise. So again, the way you can think about this is almost like a completely different operation or procedure. Okay, just happens to have the word multiply, and it happens to use this idea of multiplication at some level, but it's a different beast, right? So what this looks like here is when you want to multiply a matrix A, and now in this case, the dimensions have to match. So now what we're going to do is we're going to say A has to be dimensions M, not by P like we had earlier, but let's say it's M by N, okay? And you're going to now have to multiply this with another matrix B, which is the same size, right? So now this turns into an M. And what this does is it produces a matrix C of dimensions M by M, right? So we don't have to deal with this funny mnemonic any longer about matching the inner dimensions and producing the outer dimensions. It doesn't matter. This is a lot simpler in the sense that all you do is you now have a matrix which is some size. You're multiplying it by another matrix of the exact same size, and it produces a third matrix which is the exact same size. So this is way, way, way easier, okay? Now, let's modify the second bullet of how do you obtain this third, or the elements of C if you are given elements of A and B matrices, right? So it's really simple. It's the entry Cij is computed by basically taking the, now it's not inner dot product, it's the normal product, just a standard multiplication of, now you don't have to deal with this row and column anymore. It's you just take, oops, I should erase both of these, the product of Aij with Bij. So literally you are just multiplying each element with the corresponding element in the other matrix, right? So the rules for this is exceedingly simple. So let's look at an example. And in fact, yeah, so, okay, this example is totally different now, right? Because now we need matrices of the exact same size. So let's erase all of this. Actually, I think I can do this live. This is not very difficult. Let me leave some of this other stuff up, though. Okay, let's go ahead and make an A matrix. Let's make this just a simple 2 by 2, right? We don't care because all we care about is this thing has the same dimensions. 1, 2, 3, 4. Whoops. Let me move this over to make this a little bit more clean. 4, like that, right? And then here's B. It's got to be the exact same size, so it has to be a 2 by 2. Let's just keep going. 5, 6, 7, 8. Something like this, right? And now C is going to be, now this is where it's interesting. Our notation is a little bit failing, right? Because we saw earlier, if I wrote this, this means standard matrix multiplication where I got to multiply rows by columns and all of that kind of jazz, right? So I'm going to write this as dot star, okay? And this is trying to denote, what I'm trying to write here is this is writing down as element-wise multiplication, okay? That's what I mean by this operator, and because I need to do that to be explicit so that we know the difference between these two types of multiplication, right? This notation is also going to make a lot more sense if you watch our other videos that talk about how to implement these two types of multiplication in different computer tools like MATLAB and Mathematica. So if you're interested in actually how to do that, check out these other videos. And this notation will make a lot of sense after you've watched those videos. But again, it's not a prerequisite to go on. I just want to write this down and make it clear to everyone that this is a different beast we're talking about right here. And the reason it's a different beast, right, is because now all you have to do, this is really, really simple, right, is this first element here, C11, it's just I take the 1, 1 element of A multiplied by the 1, 1 element of B, right? So it's 1 times 5. This one is now, right, 2 times 6. Now we got 3 times 7 and 4 times 8, right? So you just multiply this by this, right? And then this by this, this by this, this by this, right? Just every single element, you just multiply with its corresponding element to get the result, right? So at the end of the day, right, this thing ends up with just 5, 12, 21, and 32, right? Perfect. Now, what's interesting about this is for element-wise multiplication, right? So maybe we better insert the word element-wise, right? So now this actually is equal to each other. So, right? And again, we better be very explicit. I should write this as A dot star B is equal to B dot star A, right? So if you're doing element-wise multiplication, now order doesn't matter because at the end of the day, you're just doing normal scalar multiplication where order doesn't matter, right? So again, just be a little bit careful of some of this, right? Okay, now why don't we go ahead and let's look at this third one. All right, so the last type of matrix multiplication we should look at is matrix scalar multiplication. So this is the only case where it's okay to multiply, quote unquote, inconsistent size matrices together. So in this case, when you have scalar multiplication, all we're talking about is that you have a m by n, right, matrix, and you're going to multiply it by a scalar, which really is you can think of it as a 1 by 1 matrix if you want to. So in this case, you can clearly see that, based on these previous two definitions, the dimensions are inconsistent, right? The inner dimensions don't match. They are both the wrong, they're not the same size, all that kind of stuff. But in this case, it's okay because this is a scalar. So it's really simple to do this. All you're going to do is you're going to basically multiply this scalar number to every element of A, right? So to get the output Cij, it's you just take the scalar, multiply it by each element Aij in the matrix. So again, let's not belabor the fact because this is so ridiculously simple. Let's look at a simple example, right? Here's your A matrix. It's some n by m or m by n matrix. You've got a scalar here. So to get the product of the scalar with the matrix, and again, I'll call out here that earlier we used a different notation to denote the types of multiplication, right? Earlier we said if you don't write anything in between, that usually means standard matrix multiplication, and then I was using this dot star notation to mean element-wise matrix multiplication. But here again, in this context, hopefully it is clear what's going on because this k is a scalar. all you're going to do is take that scalar number and multiply each one of these elements. So 1, 2, 3, 4 multiplied by a scalar 2 just becomes 2, 4, 6, 8, right? So again, really, really simple, all right? So those are the three types of matrix multiplications that are possible. And again, this is where the nomenclature and notation is a little bit lacking for someone coming right into this, because what you need to do is, if you see two matrices being multiplied together in some reference textbook, you kind of have to infer based on their dimensions, based on the context and how it's being used, of which one of these multiplications you're really talking about, right? But again, it's hopefully it's going to be clear once you start getting a little bit of familiarity with this. Okay, so let's talk about some of these rules for maybe standard matrix multiplication. We already talked about the element-wise, and we can also talk about scalar multiplication. So with standard matrix multiplication, right, we saw this is the full-blown inner product, dot product of rows and columns, and this one is the most interesting. So we've got properties like this, right? If you have A times the quantity B times C, it's actually the same thing as if you would do the A, B first and then multiply by C, okay? We got to be a little bit careful with the distributive property, so to speak. If you have something like the sum of A and B, and then you are going to write multiply by C, yeah, you are totally able to distribute this C into A and B. You just got to make sure that it stays on the right of both of these. So this becomes this, where the C is right multiplied to both the A and the B. And conversely, if the C was on the left of this sum of A and B, you just got to maintain that directionality, because as we saw earlier, in general, AB is generally not equal to B times C, right? So with standard matrix multiplication, the order matters. You cannot just flip-flop. So again, you just got to make sure you're keeping track of that, right? Now, if we're doing scalar multiplication like we just talked about, same thing. If you have a scalar lowercase k or lowercase q, a lot of this stuff falls through, and I don't think it's worth reading out every single line of these. You can take a look at these, and you can see they make pretty good logical sense what's going on here. So, with that being said, I think that is a good discussion on the different matrix multiplication ideas. Let's talk about a few more extra operations you can do with matrices. So one operation that's going to be very useful in the future is known as a transpose or a matrix transpose. And all we're doing here with this is you are basically taking a matrix and you are switching the rows and the columns. So if it used to be a row, you're going to turn that into a column and vice versa, right? So it's denoted with this superscript capital T. So what you can see here is this matrix B is the transpose of matrix A. Okay, so it's really quite simple. Again, let's look at a concrete example. So let's say you've got a 2 by 3 matrix that looks like this, right? It's A, B, C, D, E, F, right? And now if I want to take its transpose, all that means is I like to think of it as just, grab this first row, right? This first row now becomes the first column, right? And similarly, the second row becomes the second column, right? So it's really that simple. And you can also think about it the other way if you like, right? It's all we're talking about is just switching rows and columns. You could alternatively think of this operation as, okay, let's look at this first column here of A, and I will turn that into the first row of its transpose. And same thing, take this second column, it becomes the second row, right? So all you're doing is just sort of flipping the matrix. You can kind of think of it 90 degrees, right? Or just transposing or switching the rows and the columns of a matrix. That's all there is to it. So with that framework in mind, we can think of there's a couple of rules that come out of matrix transpose. So for example, if you take a matrix, you transpose it, and you transpose it again, you get back the same matrix that you started with, right? It makes perfectly good sense. This first transpose switches the rows into the columns. The second transpose takes those columns, turns them back into rows, so you get the same thing. Awesome. Let's say you've got a sum. You're adding these two, A plus B, and you want to take the transpose of the result, right? Well, that's the same thing as if you were to transpose the A matrix first, transpose the B matrix as well, then add them together. You get the exact same thing. Right? Here, let's talk about scalar matrix multiplication. Let's say you got a scalar and you're going to multiply that by A, and then you want to take its transpose. Well, that's the exact same thing as you just pull this constant or this scalar out of the transpose the matrix first, then multiply by that scalar. It's the exact same thing. This one is interesting. Let's say you got a matrix multiply. Now remember, you got to remember, this is now a full-on matrix multiply. And again, you kind of got to infer that from the context. You know, this is an uppercase versus this was lowercase uppercase. So I'm going to infer that these are both matrices, right? If these are both matrices and their dimensions are consistent, what I can do is I can do the matrix multiplication and take its transpose. Or the other way you can do that is you actually are going to flip the order. So I'm going to do B transpose and then A transpose. So this is an interesting property, and this is one that can come in handy a little bit later. But again, all this is talking about, you can prove all these to yourselves pretty easily based on the rules we've already established, but all the transpose is doing is flipping rows and columns, and this is going to come in handy in some of our future discussions. All right, so to close out, let's talk about a few special matrices that you might run into. So one special type of matrix is sometimes referred to as a symmetric matrix, and this is a matrix that has the property that when you take its transpose, you get the exact same thing. So in other words, the matrix is symmetrical across the diagonal, okay? A related type of matrix is what's referred to as a skew symmetric matrix, where you take its transpose and you almost get the same thing, but with a negative sign in front, okay? A diagonal matrix is something like this, where the only non-zeros are on the diagonal of the matrix, and everywhere else you have zeros, okay? Some of these entries on the diagonal are allowed to be zero, and you still have a diagonal matrix, but you know, something like this, you could have something like a 0 here. But as long as the non-zero entries are on the diagonals and zeros are everywhere else, you're totally fine, right? That's what's referred to as a diagonal matrix. A special type of diagonal matrix is the identity matrix, where the entries on the diagonals are all ones, okay? And we're going to see this acts effectively a lot like a scalar 1 or a scalar unity, but just kind of the matrix equivalent of it, right? While we're talking about diagonals, an upper triangular matrix is a matrix which looks like it has all of the non-zero entries are either on the diagonal or on the upper sort of half, this triangular half of the matrix, right? And everything below the diagonal, below in that sense, in that triangle of the matrix in the lower left, is all zeros, right? And conversely, the flip side of that is what's referred to as a lower triangular matrix, where you have the non-zero entries below the diagonal, and the upper half of it are all zeros, right? So this is referred to as a lower triangular matrix. So with that being said, I think this is a good spot to leave it. This is going to set the framework and the groundwork for a lot of future discussions. In fact, in our very next video, we're going to talk about extending some of the ideas to talk about the row and the column space and the rank of a matrix. And that's going to lead into discussions of things like eigenvalues, eigenvectors. Like, matrices show up all the time in mathematics, and then once we understand the mathematics, you're going to see that this also falls and shows up all the time in practical engineering applications like dynamic systems, stability, all sorts of other types of topics. You'll see matrices popping up over and over. So today I just wanted to lay down some very simple framework for it, and we're going to expand on these ideas in some of our subsequent videos. So with that being said, I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. If you scroll a little ways down and click on that subscribe button, it really helps me continue making these videos. And remember, the new videos come out every Monday, so I hope we'll be able to catch you at one of these future discussions and we can all learn something new together. So until then, I think I'll sign off. Talk to you later. Bye.